About instruction set of 8051 microcontroller. Initially, let us see what is an instruction. Later on, we'll go with the types of instructions present in 8051 microcontroller. So, instruction is an order or command given to the processor by the program, and based on those instructions, the processor is going to perform a task which is specified by the user. So 8051 has totally 111 instructions. So we'll see what are those instructions. So there are 5 types of instructions which are supportable by this 8051 microcontroller: data transfer instructions, arithmetic instructions, logical instructions with bits or bitwise logical instructions, we can also say it as, and branch instructions. So let us start this with data transfer instructions. So data transfer instructions, which are nothing but these are the instructions which are mainly used for copying the data from source to the destination. Now here source and destination might be a register, it might be an immediate operand, it might be a memory location. Okay, so and data can also be transferred to the stack with the help of push and pop instructions, and these two instructions will also come under these data transfer instructions. Okay, so let us see different possibilities with this move instruction. Okay, so here move a comma rn. Now here a is nothing but an accumulator, and rn indicates any register from r0 to r7 in the selected bank. Okay, now here what happens when you write this instruction? The contents of rn will be copied into a register, that is accumulator register. Okay, and it is a 1 byte instruction. Okay, next move a comma @ri, which is nothing but the value at address ri would be copied into accumulator register. Okay, initially ri would be storing one value that is considered as an address, and the value which is present in that particular address would be copied into a register, and it is also a 1 byte instruction. Move a comma # with x. So here x is a data value. Okay, and as it is we are using a # before this x, it would be considered as a data value, and that value is copied into a register. Okay, and move rn comma a. As I told you that rn is nothing but here any register from r0 to r7, therefore contents of a gets copied into the specified rn register. And rn comma #x, now this immediate value will be stored inside this rn register. Now move @ri comma a, contents of a gets copied into the location which is specified in this ri register. @ri comma rx, here contents of rx gets copied into the location which is specified in this ri register, and same again the immediate value gets copied into this the location which is specified in the ri register. Okay, and here ri can be either r0 or else r1. Now move dptr comma x. Dptr is a data pointer. Now this immediate value will be stored inside this dptr, and it is a 3 byte instruction. Okay, as we know that dptr is a 16-bit register. Move c a comma @ a plus dptr. Now here initially the value present in dptr along with the contents of a gets added, and that value will be considered as an address because it is preceded with @ symbol. So the value which is present in this particular address will be copied into accumulator register. Okay, that is specified here, a plus dptr, and the value inside this address will be stored inside this a register. And move c a comma @a plus pc, which is similar to move this instruction, but the only difference is contents of pc gets added with a, and the value at that particular address gets copied into a. Move x, now this is the instruction which is used for accessing the external RAM locations. As we know that move c is used for accessing ROM locations, now move x is used for accessing external RAM locations. So here move x a comma @ri. Now if you are using ri, so what happens here is the value in this ri would be considered as an address, and the value present at that particular address gets copied into a register. Okay, and move x a comma @dptr, so value at address dptr would be copied into a. Move x @ri comma a, same thing, contents of A will be copied into the address of address present inside this array. And it is again similar, move x at the rate dptr comma a, so contents of A will be copied into the address present in this dptr. Now push rx, so push directly addressed rx register on stack. So here rx indicates an address, it indicates the address of a register. Okay, for example, if I want to insert the data item present in this R0 register of bank 0 into the stack, then I have to use push 00, which is nothing but the contents present in 00 location will be inserted onto the stack. Okay, so push rx, here rx indicates addressed rx register, directly addressed rx register. Now pop rx is nothing but the top of stack is popped and stored inside rx register. Now exchange a comma rn, so it is going to exchange the contents between a and rn, which is nothing but swapping. Okay, and exchange a comma at the rate ri, so it is going to exchange the contents between a and value at ri. Okay, value at ri in the sense ri internally contains an address. Now whatever the value that is present in that address will be exchanged with a. And exchange d a comma at the rate ri, it is going to exchange only the 4 bits in accumulator with indirectly addressed register. Only 4 lower bits, that is nothing but the lower nibble, will be exchanged. And next we have arithmetic instructions. Now these instructions will perform some operations, and after execution of the result, the result is stored in the first operand. Okay, like these instructions will perform like addition, subtraction, multiplication, division. Okay, let us see those instructions. So add a comma rn, contents of rn and a are added, and again the result will be stored inside the destination. Here this position would be considered as a destination. Okay, add a comma at the rate ri, so it's an add, so a plus ri, and it would be stored inside the a. Now add a comma immediate value, so immediate value will be added with the contents of a, and the result is again stored inside the a. Add with carry a comma rn, so it is going to add contents of accumulator along with rn and the carry. Okay, if there is any previous carry, that will be added with the help of this add c. So carry flag will be added along with a and rn, and the content again will be stored inside, or the result will be stored inside the a register. Add c a comma at the rate ri, so value at the address will be added with a, and again along with carry, and again the result will be stored inside a. Add c a comma immediate value, so immediate value, accumulator content as well as carry flag will be added, and the result will be stored inside a register. Now subtract with borrow a comma rn, therefore so here a minus rn minus carry, if there is a borrow then 1, then it would become 1, therefore the resultant value will be stored inside a. Now subtract with borrow a comma at the rate ri, so here it does the same thing as we have discussed for add, that is value at ri subtracted from a as well as the carry or borrow, and the result will be stored inside a register. And the same way with an immediate value. Increment a, so it increments this particular register, and the result is again stored inside a. Increment a particular register, that is R0 to R7, so and again the result will be stored in the same register. Increment at the rate ri, which means value at address will be incremented, that is ri would be storing one address. Now the value which is present in that particular address gets incremented by 1 and again stored in the same address location. Now decrement a, it decrements and then result will be stored inside a. Decrement rn, so here rn again R0 to R7, value will be decremented and result will be stored inside rn and the same register. Decrement at the rate ri, similar again. Increment dptr, which is going to increment dptr, and again the result will be stored inside dptr. Now mul ab, now it performs multiplication between a and b, and the result will be stored in this way, that is higher bits or else MSBs are stored inside B and LSBs are stored inside A. Okay, and division AB, now it performs the division operation between A and B, that is A is divided by B. Okay, now quotient will be stored inside A and remainder will be stored inside B. DAA, that is decimal adjust after of accumulator according to BCD code. If there is any invalid BCD code, then we'll get a valid BCD code with the help of this DAA instruction. Now let us see logical instructions. These instructions perform logical operations between two register contents on bit by bit basis. So they are going to perform the logical operations on bit by bit basis, like logical AND, logical OR. Okay, let us see those things. After execution, the result is stored in the first operand, which is similar again to arithmetic instructions. Now ANL, which is nothing but AND logical. So perform AND logical operation between A and Rn. So it performs AND operation between A and Rn, and the result will be stored inside A. Okay, and the logical operation between A and @RI, that is value at address. So and again the result will be stored inside A. ANL, A comma immediate value. So it performs AND logical operation between 8-bit immediate value and A, and the result is again stored inside A. So RX comma hash X, that is immediate value. Okay, so directly addressed register will be ANDed with 8-bit immediate value, and the result is again stored in the same RX. Now it is an OR logical operation which is similar to AND, okay, but it performs a plus operation. Okay, now we have XOR operation. XOR operation, again A comma Rn, which is nothing but it performs XOR operation between A and Rn, and result is stored in A register. So it is again the same thing, that is directly addressed register is XORed with A, and result is again stored inside A. Okay, and here value at address will be XORed with A register, and the value is again stored inside, that is the result is again stored inside the accumulator register. Okay, now this time immediate value, and we can also use this kind of combination, that is Rx comma A, where accumulator contents are XORed with the specified register, that is directly addressed register, and then the result is again stored in the same address location. XOR L Rx comma hash X, immediate value is XORed with the directly addressed register, and again the result is stored in the same register or same address. Now clear A, which is going to clear the accumulator, which is going to initialize the accumulator with zeros, and complement A, so it performs the complement operation, that is one's complement operation, that is in the negation operation. Zeros will become 1 and ones will become zeros. Now swap A, it performs swapping operation inside the accumulator register, which is nothing but lower nibble will be copied into higher nibble, and higher nibble gets copied into lower nibble. Okay, and rotate left A, which is nothing but AN is copied into AN plus 1, and A7 is copied into A0. So here it forms a rotate operation, which is nothing but if this n is 0, so A0 will be shifted to A1, and A1 will be shifted to A2, A2 will be shifted to A3, A3 will be shifted to A4, A4 will be shifted to A5, A5 to A6, and A7 is again shifted to A0. This is what means a rotate operation. And rotate left including the carry. So what happens here is AN is shifted towards AN plus 1, and carry is shifted into A0, and A7 is shifted into the carry flag. Okay, so here if AN is considered as n value is 0, so A0 is shifted to A1, and carry is shifted to A0, and A7 is shifted to the carry. Now rotate right A, which is again similar to the left, but here this time it operates in the reverse form, that is AN plus 1 is shifted to AN, and A0 is copied or shifted to A7. Rotate right through carry, again it is including the carry flag. Now let us see logical instructions on bits or bitwise logical operations. These are similar to logical operators, but the only difference here is they perform only on the single bits, that is bit addressable area. Okay, they perform only on the bit addressable area. Now here clear C, which is going to clear the carry flag. Okay, clear bit. So the specified bit will be cleared. Set B C, which is going to set the bit carry flag. Okay, set B bit, so it is going to set the specified bit, addressed bit. Okay, and complement C, carry flag gets complemented, that is 1 becomes 0 and 0 becomes 1. Complement the bit, the specified bit gets complemented. ANL C comma bit, so it performs logical AND operation between the specified bit and the carry flag. Okay, ANL C comma complement of bit, so it performs logical AND operation between the carry bit and inverted directly addressed bit. So ORL C comma bit, it performs OR operation between the specified bit and the carry flag. It performs OR operation between the complemented specified bit and the carry flag. Move C comma bit, so it moves directly addressed bit to carry bit. So whatever the content present in the specified bit gets copied into the carry flag. Move bit comma C, so carry flag gets copied into the specified bit address. Now let us see program flow control instructions. Now these instructions are mainly used for transferring the control from one location to the other location, or from one address to the other address. Okay, let us see some of the instructions for this. So here we have a call. These call instructions are mainly used in case of functions. Whenever we want to call a function, whenever we want to call a subroutine, then we are going to use these call instructions. Now here a call is nothing but absolute call, and here the address is of 11-bit size. Now what happens whenever you whenever this particular instruction is executed? Now program counter plus 2 will be copied into program counter, and then stack pointer gets incremented by 1, and this PC lower byte will be copied into the stack pointer, and then stack pointer gets incremented by 1, and again PC higher byte gets copied into stack pointer. Okay, so it means as we have called a function, as we have called a subroutine from the main function or from the main program, now what happens here is control will be transferred to the subroutine. Okay, now before the transfer, what happens here is program counter value will be stored inside the stack. Okay, and this particular storage inside the stack is called as a return address. We are storing the return address. Okay, and L call is nothing but long call, and here the address is of 16 bits. Okay, so whenever this instruction is executed, then PC plus 3 will be inside this program counter, and lower byte will be copied after incrementation of this SP, and then after again incrementation of SP, higher byte gets copied, and the address gets copied into program counter. Now we have a return instruction. So call instruction is used for transferring the control from the main program to the subroutine, and return instruction is used for transferring the control from the subroutine to the main program. Now it pops the value which is previously inserted onto the stack, that is stack pointer value will be copied, that is top of stack will be copied into PC higher byte, and then stack pointer gets decremented by 1, and again this top of stack gets copied into lower byte of the PC, and again stack pointer will be decremented by 1. Now RETI, which is used for returning the control from the ISR, interrupt service routine. Okay, now the same operation goes on, that is stack pointer value gets copied into higher byte, it gets decremented by 1, and again the stack pointer value that is whatever the value that is pointed by the stack pointer will be copied into a lower byte of PC, and again it is decremented by 1. Now a jump, it is a unconditional jump, that is absolute unconditional jump instruction, and it transfers the control to the specified address. Okay, and it is 11-bit address, therefore here PC plus 2 gets copied into PC, and that particular address will be copied into 0 to 10 bits of program counter. Why? Because it is specifying only the 11-bit address. Okay, now long jump, which is again an unconditional jump, so it specifies a 16-bit address. Now that particular address gets copied into program counter. Okay, and then short jump, okay, it jumps to the specified relative address, but its range is from -128 to 127 locations. Okay, now jump if carry to the relative address. So what happens here, if at all this particular carry flag will become 1, then it jumps to this particular specified location or specified relative address. Okay, so that relative address gets copied to the program counter. Now jump if no carry to the relative address. So if there is no carry, that means if C is 0, then then the control will be transferred to the this particular location, that is relative address location. Now JB bit comma relative address. So jump if bit addressed bit is set. Okay, so if at all this particular bit is set, if at all the specified bit is set, then it jumps to the relative address. JBC bit relative address, it means jump if addressed bit is set and clear it short jump. So it has to jump to this relative address whenever this particular bit becomes 1, and while jumping to this particular location it has to clear this particular bit. And then we have jump @a plus dptr. Now it is going to jump to the specified location, which is formed by adding the contents of a and dptr. Okay, and jump if 0 to the relative address. So if at all this accumulator is 0, then the control will be transferred to the specified relative address. Now jump if non-zero to the relative address. If this a is not equals to 0, then control will be transferred to this relative address. CJ and E, that is compare, and jump if not equals a comma rx comma relative. Compare the contents of accumulator and directly address register rx, and jump if they are different. Okay, so it will compare initially the contents of a with rx. Okay, that is the directly addressed register, and if both are not identical or both are not similar, then it jumps to this particular location. Now decrement jump if non-zero, rn comma relative address. So here it will check whether this rn register is equals to 0 or not. If this is not equals to 0, then it jumps to this relative address, and then it decrements this rn. So for every operation it compares this rn and decrements this rn, and then jumps to the relative address. If this rn becomes 0, then this particular instruction will be bypassed and then moved on to the next instruction. And then we have a last instruction, that is no operation. So whenever the processor executes this instruction, it will not perform any kind of operation. Okay, and these are the complete instruction set of 8051, and by using these instruction set we can write the assembly language programs. Okay, thank you.